Let me give you this graph here. So I'm going to give you the acceleration time graph. Whatever we're talking about here, it has an acceleration of 3. So we could be talking about us standing on top of a building, dropping, let's say, a cannonball. Or it won't be Earth. It would be on a different planet where g is 3. So when you're given this acceleration time graph where the acceleration is 3, all that you know looking at this is that something is traveling faster and faster, uh, faster and faster. Every second it would have increased in speed by 3. So just this graph alone, all that you know is that something is traveling faster and faster by 3 whatever is in front here, by 3 meters per, well, something's traveling faster and faster by 3 meters every second. Okay, so just by this acceleration time graph, all that you know is that something is traveling faster and faster every 3 seconds. So it could be you standing on top of a building and dropping a cannonball, and this cannonball is dropping. Well, the speed will increase by 3 every second. Or you could, well, remember when you stand on top of a building, it won't be Earth because Earth is 9.8 or 10. But this here is 3, so it must be on a different planet. So, well, all that you know is that something is traveling faster and faster, well, by 3 every second. So it could mean your dad sitting in a car and he puts his foot on the accelerator, so he's accelerating by 3 meters per second squared. So all that you know, looking at this, all that you know is that something is traveling faster and faster and faster. The speed increases by 3 every second. That's all you. That's all that you know. So well, if I give you this acceleration time graph and then I'll ask I ask a question: what is the distance traveled after, let's say, 8 seconds? You see, for just this acceleration time graph alone, there isn't enough information for you to answer that question. What is the distance traveled after 8 seconds? Because let's take this scenario here. Um, it's just like, let's say your dad. Well, given this graph here, all that you know is that something's traveling faster and faster every. The speed increases by 3 every second. So let's have a look at your dad's case here. Your dad is sitting in the car. Let's say this graph represents your dad's case sitting in the car. Okay. Now this car is at rest. So and then let's have a look at a different scenario where your dad is when it's time t equals 0, your dad is already traveling at 100 meters per second. So he's traveling really fast in this second scenario here. This is your second scenario. This is your first scenario. And in the first scenario, he's going well, he will still have an acceleration of 3 meters per second squared. This one here is still an acceleration of 3 meters per second squared. But the second scenario is when time equals 0, he's already going at 100 meters per second. Here, when time equals 0, your dad sitting in a car is traveling at 0 meters per second. So you see, if you get to the first person to get to the finish line, well, they're both still your dad. But this second scenario here, the second scenario will just whiz past here, whereas this one here is it's stationary when t equals 1, and then it needs to build up speed. So it's still traveling faster and faster, but it's the car's at rest, so it needs time to build up speed to get to the finish line. Whereas in this second scenario here, he's already going at 100 miles an hour. So while he's still traveling faster and faster, but because he had an initial speed, he's just going to whiz past in the second scenario. Whereas in the first scenario, he's going to, well, he's really slow at the start, and then he's going to speed up and speed up. Well, anyway, the second scenario, let's say this is a distance of let's say 700 meters from here to here, 700 meters, 700 meters from here from here to here. Put your money on the second scenario, because well, this one he has to start from rest and then slowly build up speed. So given this graph alone, this acceleration time graph alone, all that you know is that something's traveling faster and faster. So you see, in order for me to ask you how far, what is the distance covered after 8 seconds, I need to give you some initial conditions. I need to tell you that, oh, by the way, your dad sitting in a car traveling at 3 meters per second squared. When time is 0, his speed is 0, and also his distance is 0. So his distance is 0. You see, I need to give you these two pieces of information in order for you to answer this question. But just by looking at this graph. So this here, all that you know is that something's traveling faster and faster. I need to give you some initial conditions. Here, here in the second scenario here, I would say, oh, the speed, when t equals 0, speed is 100. Distance is 0. So I need to give you some initial conditions. Okay. So let's just look at this first scenario here. Okay. My question in this video is, given this acceleration time graph, which is you know the acceleration is 3. Now the initial conditions are, well, the speed would be 0 when time equals 0. The speed is 0 and the distance is 0. Now you've got enough information to answer the question. What is the distance traveled after 8 seconds? Okay. So hang on. Let me write this down. So when t equals 0, speed equals 0 and d equals 0. Okay. So these are the initial conditions, and the graph here. Well, the acceleration is 3. So now I can ask you a question. What is the distance traveled after 8 seconds? So press pause and have a go. Okay. So when you're given a graph, inside your mind, visualize. Sorry, I'm trying to find a blank space. Visualize when you're given the acceleration time graph, inside your mind, visualize this: acceleration time, speed time. And then you've got your distance time. This is, in most cases, this one's useless. This is the most important one here, because from this you can work out the distance traveled by working out the area underneath the graph. So here your acceleration is 3. Okay, that means your speed graph will be y equals, well, the gradient will be 3t, or what? 3t or 3x, it's up to you. Alright, I'm going to use 3x, it doesn't matter. No, really I should be using s equals 3t, but for some reason I like x, I like y and x. Well, anyway, this line here would be y equals 3x. Okay, and then if you want to know the distance traveled after 8 seconds, well, look at this, 8 seconds here. So here you basically when you're in the speed time graph, the distance traveled will be the area underneath the graph. Okay, so when we started, all that we were given was this graph here. So from this graph we jumped to this graph. Okay, now you want to know the area underneath the graph. So this height here would be put 8 into this thing here. Okay, so it will be the height here will be 24. The across here is 8. Okay, so it will be a matter of 24 times 8, and then divided by 2, because it's a triangle. So it's 24 times 8 divided by 2. I'm just going to say 24 times 4. 24 times 4. So that's 24 times 4. So that would be 16 carry the 1, 8, 9. So this area here will be 96. Okay, 96 watts. It will be 96 meters. Okay, so given these initial conditions here, the distance traveled after 8 seconds will be 96 meters. Okay, so when we first started, we were given this graph here. From the acceleration time graph, jump to this, and then from your speed time graph, you can work it out here. You see, from this time graph, you can actually translate it to this time graph, but it's well, let's just use this speed time graph. It's a lot more useful. Okay.